Hey everyone, nice to meet you all. Hope you are having a good day today. I'm Nidhin. I'm currently a machine learning engineer at Walmart. So today, let's go over chapter 7 of the book. So as Ted mentioned, we will cover ensemble learning and random forests. So the main topics that the book covers are voting classifiers, bagging and pasting, random forests, boosting, and stacking. So, what is an ensemble? So, in previous sessions, we learned about building different classifiers like decision trees and support vector machines. So ensemble is just grouping these predictors together. And each of these predictors individually gives a prediction. So how do you combine the output from all those classifiers or regression models? So ensemble learning has different methods that you can combine the predictions, either with bagging, boosting, or stacking. And ensembles generally work when the predictors are independent from one another. So like like either different models or like trained on different subsets of the data. So the first thing the book covered is like voting classifiers, right? So in this diagram here, so we have 4 different classifiers, and for one prediction instance, 3 of the models predicted class 1, and the third classifier predicted class 2. So how do you basically take a final prediction from it? You can just take a majority vote here. So in this case, it's 1. So that's the simple thing. You don't consider how confident the classifier is for each prediction. You just take the majority. The next one is soft voting. So basically, here we have 3 classifiers. So model 1, for class 0, it gave it 20% confidence. Class 2, it gave it 80% confidence. And assuming you weigh each of these classifiers with equal weights, what you basically do is, so equal weights, so 3 classifiers, so that's 33% for each of these votes. For class 0, model 1 predicted 20%, model 2 predicted 10%. So you just weigh their scores and then combine it. So in the end, the model predicted 36% for class 0 and 62% for class 1. Yep. So that's basically the 2 different types of voting. And Scikit-Learn generally just makes it very simple. You can just import the voting classifier from the ensemble module, and you can give it the hard or soft. And and that's basically it. And one thing to note is, like, if you look independently for these models, like they all maybe a little bit around the same range, but when you kind of use like the wisdom of the crowd, or like when you combine them together, they give a slightly higher a high accuracy score. So that's basically voting. That was the first section that the book covered. Before we go into the next section, like whether any questions or anything, or okay.
Could you, Nadine, sorry, can you go back to the slide where you had the percentages for the soft voting? So is that, so for example, for 0, is the 0.2% would be if it's the negative class, and the 80% is if it's the positive class. Is that correct?
Yes. So for this line, probability of class 0, so each of them have 33%. That's where the 0.33 is coming, and the 0.2 is coming because for class 0 it's 20 class, and then for model 1 it's 10% and 80%. Yep.
Okay, so the final probability would give us a probability for both then.
Yes, so like for the ensemble classifier for class 0, we would give 36% for class 0 and 62% for
Okay,
class 1.
thank you.
Yep. Cool. So the next thing in the section the book talked about was bagging and pasting. I have to say I've never heard of pasting before, but yeah. So previously when we talked about the voting classifiers, we didn't make any mention on like whether we had like each of the classifiers, if we are training on the whole data set or a subset of the data set or anything like that. So what bagging is basically, you bagging and pasting, you both sample your data set. And in the case of bagging, you sample, but you do, you allow replacement so you can possibly see the same training instance again. And pasting is just sampling without a replacement. And again, so how does this compare with training on the full data set? So, if you use sampling, like your individual predictor might obviously have a higher bias, so it might underfit your problem. But because you're creating an ensemble, like you will definitely have lower variance than if you just had a single classifier that was trained on the original data set. And just an example to show this. So on the left-hand side, you have a decision tree, just a single decision tree. And on the right-hand side, you have a decision tree that is an ensemble of 500 trees. So you definitely see like the decision boundary is more generalized than like what you just see in a single decision tree. So so one of the nice things about like bagging, especially when you are training an ensemble, is so we're all familiar with like validation data set and getting a validation score. But one nice thing about bagging is like, so if you're training three classifiers and you're doing bagging, so let's assume in your data set we have 4 training instances. So with like bagging, what you might have, bag 1 might see if you sample 4 instances. So in this case, patient A was sampled 2 times and patient C was sampled 2 times. In bag 2, you were luckily able to sample each of the training instances at least once. And in bag 3, the subset that you saw was patient A and 3 times patient D. So your classifiers will definitely see different views of the data. But one nice thing about the fact that the classifiers don't see the full data is that the data that was not trained on the classifier, you can actually use that to compute this score called the out of bag score, or basically how does your model predict on data that a certain, the certain classifier didn't train on. So in this case, if we take like patient D, or patient, let's say if we take patient B, for example. So patient B was only seen by model 2, right? So what you can do is you can feed in patient B to your ensemble, and you can ask classifier 1 and classifier 3, like how did it, like if you only consider the predictions from classifier 1 and 3, like how would it perform? And this is so obviously you could do it like cross validation, where you have a completely holdout data set that was not seen by any of the models, but this is another way to also get, how the model is performing. Yeah, sorry, that was a mouthful, but hopefully it makes sense where, yeah.
Hey, Nidhin?
Yes.
I have a question. I think I know the answer, but I just wanted to confirm. Let's say you're doing a classifier, okay? And so bag 1 and bag 3 and however many other bags didn't use patient B when they were trained. So patient B is out of bag for them. Do you then take all of the different models, all the different bags where it's out of bag, and you have them vote, and you take the final answer and that's what you use to calculate your out of bag error? Or do you, I think that's what you do, as opposed to if there were 5 models that didn't use patient B, you could just take all 5 of them and sort of average the error of the 5 of them. Does my question make sense?
So what was the 2 variants? The second variant was like you only take the ones that didn't see it, and you take the output from that. And
so you either take the individual models that didn't see that, and you look at the errors on all of them, or you take those models and you have them vote, and you only calculate the error on the common final answer. I wasn't sure.
So I didn't necessarily look at the code, but my understanding was you would still take the final voting for the ones that saw it. But if anyone else knows for sure, I'd love to.
Clarification question. Is there an easy way to get this out of bag sets in Scikit-Learn and do something with them?
Yeah, there is the property like OOB underscore score. So Scikit-Learn takes care of that for us.
I think I saw. Thank you.
Cool. I found the last section in this thing a little bit confusing, talking about this random patches and random subspaces. So, so far we talked about sampling the data, but you can also sample the features. So like if you use the Scikit-Learn bagging classifier, or I guess a random forest, there are some properties you can use. So if you want to sample the features, you can put bootstrap underscore features. That's a Boolean value. And then max features is kind of like an int. And if you want to sample the records, you could put bootstrap, again, a Boolean value, and max underscore samples. So I guess if you sample both training instances and features, it's called random patches. And if you keep all your training instances, but you sample your features, that's called sampling random subspaces. Yeah, I never heard of these terms, but yeah. So again, like if you sample your features, you definitely will get like more like model diversity. And again, you might underfit a little bit, but you're again trading this bias, but you get a lower variance.
Can you talk more about the sampling features? Was interesting to me, because it seems like, I don't know, what you're after is kind of the importance of the features, see which ones work best, but you can get a feature importance, or I don't know, maybe I'm way off, but somebody have more insight on the whole sampling features thing.
Yeah, so like, like when we covered like decision tree, like every time, we were looking at a split, we were considering all the features. But what you could do is, like maybe when you're making a decision, you just look at 80% of your features that are available. So that's just basically what sampling the features in the context of trees mean.
I can tell what happens with random forest as example.
Yep, sure, go ahead.
In random forest, we have default when only 62.3% of all rows are taken for particular decision tree. And you can change it. It samples with repetitions. And for features, for classification, they take only square root of the whole number of features number to take the features, and they pick up them randomly. And for regression, they took the number of features divided by 3. As you see, each time we have definitely less than half of features. What it helps is that it can happen that algorithm, which works as a greedy algorithm, will pick up, if you have a big subset of features, it will pick up a feature which immediately give a big advantage, and it cannot find a feature which will give much better advantage when you start not with this one but with another one. And okay.
So is it like when you have you'd use this more likely when you have like a lot of features? I mean, what's like a good number? Because it just doesn't seem that useful if you've got like 10 or 12 features.
Okay.
No?
You start with what algorithm offers you in this particular case with this number. And then you search around with cross-validation as usual. Because no, there is no, again, there is no rule for universal rule for any data by which you can pick up a really good parameters. Each time you need to work to find them, sorry.
Yeah, I would say that's a good intuition. Like Maya's saying, you can't know for sure. Maybe you know, by some fluke, it's really helpful on a small data set with only 10 features. But yeah, if you had hundreds or thousands or more features, you could really see the potential benefit of doing this, where you're you know, you're building models only on small subsets of the features, and especially if those features are continuous. Because what I can tell you is that if you take a data set that has 10 real columns and you add 1,000 columns of just random number generators, right? And you build trees, you're going to see that those other 1,000 columns get used fairly often. Because in any subset, you know, the odds of having one random column that does a really good job of separating things, it's pretty high. You know, they won't on average do a good job, but that at least one of the 1,000 just happens to do an amazing job. But they won't consistently get used. And so that's where, you know, sometimes by doing subsets, you can sort of force it to, you know, look at particular things. And then what you would assume is that if you had a model that was built on just, let's say, 20 of the completely random number generator columns, it's going to have a really hard time building a model. And so its guesses are pretty much going to be random. And so those models, you don't really care if you have 100 of them in your votes, because the odds are they're going to cancel each other out because they're essentially, you know, random, since they have no information. So that's sort of the benefit of being able to do this voting business, is that in terms of expected value, things that don't have good information will tend to cancel each other out.
Thanks.
Cool. Thanks, Maya. Thanks, Ted. Cool. So, yep. So now the book then talked about random forests. So in the previous section of the book, you know, we were using this generic bagging classifier, but if your model is basically a decision tree, then you can just use this random forest classifier, which just basically is a little bit optimized for the scenario where you are creating an ensemble of trees. So the random forest classifier supports all the hyperparameters that you might use of a decision tree and that you might need for a bagging classifier. And the other thing it also does is, so not just of sampling the training instances here, you can sample which features, as it allows like sampling a random subset of features when it's creating the split. And again, this allows you to build, to make your model more resistant. Like, so your model will have a low variance, but again, if you, a model that was trained on a full data set probably would have like a lower bias, but this one, again, if you decide to sample your training data and you decide to sample the features, it can have a higher bias. Then there's a small variant of the random forest classifier. So basically, when you are doing a split, instead of trying to still find the best feature that would provide the best split, what you can do is, you know, you can have like some threshold, and as long as any feature that basically meets that threshold, the extra trees classifier or model will just basically use that feature. And because of that, because you save like some extra feature computations, it is supposedly faster than random forests. One other benefit of using random forest or extra trees classifier is, and so this is a feature of decision trees itself, because based on how the tree is built, you can kind of tell how important a feature is. But you can also use this idea like across multiple trees. So basically, for each feature, you already know while you're building the tree that how useful a feature is based on like how much it's decreasing impurity. And then if you basically average all of that across all the trees in your forest, you can use that as a feature importance and just weigh the average based on like the node's weight, and we basically have a pretty good feature importance. Yeah, so that was the next section. So on random forest. Before we go to the next area, were there any questions on those pieces or? Okay. So the next section the book talked about was boosting.
Sorry, Nin, I was gonna just make a quick comment, but slow on the mute button.
Okay.
I just wanted to say, so once we get into this section, unlike, if some of you are used to doing like t-tests and linear regression and things like that. So we're now no longer in the realm of statistical models. More technically, you'll see the term, these are non-parametric models. And so there is no standard error associated with a decision tree. There is no standard error associated with a bagging set of trees or random forests. So you have the prediction, and to a certain degree, the vanilla algorithm out of the box doesn't really tell you how confident it is. So it's up to you to sort of say, do I think I have a good model or not? It doesn't really give you a metric that says, hey, I built this model, but it's mostly just guesses. I wasn't really able to build a very good model.
Yep, thanks, Ted. Cool. So the next section the book talked about was boosting. So, like if we consider like the models that we kind of previously talked about, like random forest, basically all the trees that you're training on the random forest, you can basically train them independently. Or if you're using different classifiers or different models, you can technically train them independently. But what boosting is, so the two main approaches that we'll talk about, adder boost and gradient boosting. But the idea is you're basically training your predictors sequentially. And the goal is for every new predictor that you are training, it's trying to improve on the previous one by trying to improve where the predecessor made its error. So the two common ones are adder boost and gradient boosting. And we'll have a slide for it, but adder boost basically, for each successful predictor that you're training, you want to increase the weight that you're giving on misclassified samples. And gradient boosting, basically, your training predictor, you are getting the error that your predictor is making, and then the further successful predictors that you're training, you're actually training it on the errors that the model made and trying to improve that. So let's just take a look at the steps for adder boost first. So the book had like a lot of equations, but I think I find Chris Albin's steps a little bit easier to do. So basically, you start with, let's say n samples. So for every observation, you put, let's say, an equal weight for each of them. And then what you do is you train a weak model, let's say like a decision tree. And now you got your model trained, you predict, you get like the error. So if for a sample, if you made an error on it, then you increase the weight of that observation. And if the prediction went fine, you can just reduce the weight. And then after, it's just normalize the weights. And now you train a new model again on these training instances that have adjusted weights. And the goal is like this new model that you're training is going to become better, or it's going to put more importance on these previously mislabeled training instances. So you repeat basically steps 3 and 4 for until some error condition is met, or until you build n number of trees. And I guess the only thing that's maybe explicitly not mentioned here is how to compute the weight increase and how to like what score are you giving to the predictor. But basically, this is the core of AdaBoost. Yeah, so the other variant of boosting is gradient boosting. And here I thought I'll just go through some steps. So let's say you're trying to, so this is like a regression problem. You have the age, city, and you're trying to predict someone's income. And so that's your target variable. So you train, let's say, a decision tree regression model or whichever regression model, and you get the prediction scores here in this column here. So this is your first model. So you get the predictions, you compute the residuals, so which is basically the predictions minus the target. And yeah, so this is the, yeah, so you have your model predictions and then you have the residuals. So we see for the first training instance, the actual value is 51,000, but we predict, the model is predicting 53,500, so a residual of 2,500. So the next thing you do for model 2, your y variable is going to be this residual error. So for model 2, the target, again, as I mentioned, is the residual error. And if you look at the model 2's prediction, so for row 1, the actual value was negative 2,500, but our model predicted 5,500. So at this point, if you want to get, what is your ensemble so far prediction, you basically pass in your X data into model 1 and model 2, and you get the value from model 1, and then you plus it with the model 2's outcome, which is like the predicted error, and that would be the value if you took all the predictions up to model n. And this step you basically repeat until you hit like some error target, or until you build n number of trees. So more generally, if you look at this, so again, model 0, the first model that you're training, your target is going to be the actual value, the y value from your data set. But model 1, you're basically predicting the error that you got from using the first model. And likewise for model 2, you're using the previous model's error. And if you want to get the prediction for up to model n, you just feed in the X data and just and then sum up the values. So that's basically gradient boosting. The book mentions like so Scikit-Learn has the gradient boosting classifier, gradient boosting regressor. There are other popular, like I guess, gradient boosting libraries like XGBoost, LightGBM, and CatBoost. I can't really speak about what made them really so popular, but I guess if someone else can speak to it, that's good. But yeah, XGBoost definitely is used a lot. We also use it at work a lot. And XGBoost also can be used for ranking, which is something that we use a lot at work also. Yeah, if anyone has experience or opinions on where like XGBoost or LightGBM or CatBoost might shine compared to what we saw to the typical gradient boost, feel free to share.
I can share. I've gotten far enough to know that, when you build a tree, you have a subset, and then, you decide how am I going to split that, left and right. And we talked a little bit about in the last chapter that, hey, two of the common metrics are the Gini coefficient and the entropy. I don't know the details. I just know that both XGBoost and LightGBM have different splitting criteria that they use. So it's not just a like a specific programmer's implementation of of gradient boosted trees. It is fundamentally different in the way it does the splits. So it's very reasonable then that you can imagine that you would get slight differences in performance. So I would say it's perfectly reasonable to try sort of a vanilla boosting XGBoost, light GBM, and if one of them does a little bit better than the others, it's not necessarily just random luck on that, that seed or whatever. That you will sometimes see consistently one of them will, and light GBM for me on average does better than the others. But you'll see it consistently, and that's because it's not just like, oh, it's a really fast implementation. It actually does do some things differently under the hood. It has a bunch of additional tuning parameters, but that aside, it is fundamentally slightly different.
I think the only thing I can share here is like this week, because of this section that we were reviewing, I like ran up several different models. So I like built a decision tree, random forest, XGBoost on the exact same data set. And I compared the performance, and I'm familiar and used to working with like XGBoost and random forest and decision tree in the past, but I've never just said, oh, let me take one data set and then compare those in general. So I did it because of the chapter we're reading. And so from the data set that I had, I can tell you that when I ran an XGBoost model without doing any parameter tunings, the model was at 84% accurate. When I ran a decision tree model, it was about 60% accurate. But when I went back in and I fine-tuned the parameters, so I did a technique called grid search to assess what are the optimum ways, what's the optimum depth of the tree, how many samples, should I have per leaf. It was able to get the decision tree model to a high 83%. And that was with me doing a lot of performance tuning. So just in general, thinking about the model building process, it was more work for me to get the decision tree model to generate high accuracy results. Whereas with the XGBoost model, just right out the gate, without me even doing a lot of performance tuning, I was able to get 84% accuracy. Then I ran a random forest model, and I just I just controlled the maximum depth of the tree, and I got 85% accuracy. So I actually got a higher accuracy rate running the random forest model than I did the XGBoost model. And it took the random forest model lesser time to train than the XGBoost model. So that's one of the things I know, like going into like the boosting models, they're a little bit more complex, and it does take the model a little longer to train. But one of the things that I do look at is I look at, I do, ROC for evaluation, but I look at the precision, the recall, and the F1 score of all the models and the support to assess, okay, which one is performing better in terms of predicting, my target feature. So that was just my experience with it. So, XGBoost, it'll get you a higher accuracy rate right away, but it is slower to run. And decision tree, you're going to have to do a lot more tuning your parameters to get a high accuracy rate.
Thanks, Christy and Ted, for sharing that here. Anyone else have experience or opinions about the different XGBoost different gradient boosting libraries experience? Or
another difference I've seen is that the Scikit-Learn gradient boost classifier does not handle missing values, and XGBoost it does. It can work with missing values.
Oh, nice. Yeah, that's definitely useful. Yeah.
I had a kind of a question. I've actually never used AdaBoost, and I was curious if anybody here has. I don't know if it's fallen out of favor, but they still talk about it in books, or if some people actually use it.
I've seen it mentioned various places on Kaggle, but almost always people end up just doing gradient boosting. I haven't seen eta boosting really in the wild at all.
Thanks, Ryan.
Okay, thanks, Ryan. So the next section and kind of the last section, which the book didn't really have, was stacking. So, you know, when you have all these different classifiers, how do you basically combine them? One thing we learned was basically voting, maybe putting an equal weight to the models. But what you can do is you can actually have a meta model that basically takes the output from all these models and learns the appropriate weight. So in this case, what you might do to actually train this thing, you might split your training data, let's say in half. The first half, you train each of these models individually. Then what you do for your second split of the data, you feed them across each of the models and you get the output of that, and then you feed it to this new model. And yeah, and then the model will learn how to combine the predictions from the other models. The book also mentioned, so this is just a single layer. So you have your single models, and then you have a final model that combines it, but apparently you can have multiple layers too. But I've never really used it that way. Does anyone have experience with stacking, let's say more than one level, or just stacking in general? Or
I've done work with various different levels of stacking. And the way that I view it is you're basically taking the output predictions from multiple different models, and then you're treating it as features into a new model, and then you can roll that forward more iterations and have more layers of models. In general, it's kind of dangerous because if you're fitting based on outputs from previous predictions, it's difficult to properly validate that. You end up running in trouble where you're training across your validation set potentially multiple times, and then you're just overfitting your data. But there is definitely occurrences I've seen where doing that has yielded better performance. It just makes things much more complicated.
thanks.
I've always conceptually liked the idea that maybe there's this corner of the feature space that has some interesting properties that the stacked meta learner, right, can understand. So the way I describe it is like, you're predicting housing costs, and so for really large houses, they behave differently. And so then it can say, for big houses, I'm going to trust model 1 more. For small houses, I'm going to trust model 2 more, right? That's like a nice little pet theory, but in practice, I haven't actually seen it work, because obviously model 1 can also in itself just do things differently for small houses and big houses. You don't necessarily need a meta model to just tell you that, right? So I haven't done it extensively, but the few times that I've played with it, complicated stacking didn't necessarily do much. And then, in terms of like Kaggle competitions, I have certainly seen write-ups where people have done stacking for the top winners, but again, oftentimes that's because they're trying to win a contest and they're trying to squeeze that last 0.0001 out of it. At work, if you have a model that's 96% accuracy, you wouldn't do all of that computation and effort to get it to 96.0001. So.
So one other thing about stacking too, the variant that they show here is you take your input data, you pass it to all of your models create some predictions, and then those get passed to a meta learner. There's also a variant where you take the data and you pass that to the meta learner as well. And so the theory behind that is kind of what Ted was talking about, where you have these models, they're all creating different predictions, and then you have the data into the meta learner. And with that initial data, your meta learner can potentially learn during this data condition, this model is the most accurate, and it can sort of filter. And the analogy that I frequently hear is like, imagine it's a bunch of students and then the meta learner is a teacher and they know what subjects the student is best at, and then the teacher can basically call upon the different students to answer different questions in different amounts. But like Ted was saying, it's kind of a nice story to tell, but in practice it doesn't really end up like that.
Yeah, thanks, Ted. Thanks, Ryan. Yeah, I didn't know about that variant here.
One other comment, there's actually a much simpler kind of stacking you can do. So Nidhin, you mentioned soft voting, right? So let's say I'm predicting classes and I have different probabilities. I can just average all the probabilities for mine. But one thing you could do that's just slightly more complicated is you could do a weighted average. You don't have to weight all your models equally. And so that would be technically it's a stack, but it's not a super complicated stack, right? So whether you do it with just simply figuring out some weights, or you just assign it a very simple linear regression where each model's predictions gets just a linear weight. That way, you're highly constraining that meta learner so that it can't do some goofy overfitting thing. It just gets to basically decide. And for something like that, then it's using static weights. It's not saying what Ryan was just talking about, like, oh, for this kind of problem, I'm gonna give model 1 more weight. For that kind of data, I'm gonna give model 2. But you're just simply saying, hey, you know what? I built 4 models. They're not actually all equally good. Model 1 actually is better. So I'm gonna give it, 40% of the weight, and the other ones I'm each gonna give 20% of the weight. And so it gets more votes than the others.
Thanks for that. Thanks.
Sorry, can I ask a few questions? So for multi-layer stacking, is that similar to what's happening in the forward process in neural networks, or no? I know we haven't gotten to that yet. Just wondering.
Thank you for that question.
I would say not really, because in this, if we're thinking about layers like that, these initial models, these are already trying directly to predict the output. In a neural network, all of your intermediate layers are just outputting numbers. It's not necessarily that they're trying to make a prediction with all of those outputs. It's just trying to transform the features. So in that regard, it's slightly different, and you're not in a neural network, you're passing the information a lot more directly through it. There are similarities, like the way the layers are kind of passing information along, but I wouldn't, it's not operating in the same way. I wouldn't say that.
And then I was looking at the code in the gradient boosting section on page 206. I understand it says to get the best n estimators, looks like we get the minimum error, but then it does +1. Why do we add +1?
I think that's just a Python thing, because Python always is 0 indexed. So if you say I used models 0, 1, and 2, you used 3 models. So if you ended at model 2, then you add 1 just to say there's a total of, when you change it to counting numbers, they're always 1 indexed. So I think that's all that +1 is doing, is just trying to turn it into human understandable, like use 3 things, but they're numbered item 0, item 1, item 2. Does that make sense? Is that what you were going to say, Ryan?
Yeah, I had a similar belief. It's probably just that the counting starts at 1 instead of 0. So you start with 1 tree instead of 0 trees, and so their indexing is just off by 1. So you need to add that at the end to make sure you get the same result.
If you look at the code, the next thing they do is pass it along as a parameter to the next function. And then you're saying, give me the top n. If you pass, you have to use the counting numbers to get the top n.
Can I ask the last one? I saw in this diagram, Nidhin, you used the term blender. In our book, it uses, what does it use? You used, what is it, meta? I have the thing in the way. Sorry, yeah, use meta learner. Is meta learner the same thing as blender?
Yeah, I mean, at least I'm using it the same way, but
okay.
It's funny because there's differing opinions. Depending on who you talk to, they will define some of these terms differently. I would say that a meta learner is like just a general concept of a second layer combination of different models. And then my interpretation of blending, I've had conversations with my coworkers about this, and they have different definitions, but what people seem to agree upon is blending is more of like a simple linear combination, and then stacking is when you do a more complicated model, like if you have another neural network built on top of it, or a light GBM or something else. And a blending is just like a weighted average or something like that. But that's not set in stone, I would say. People use that differently depending on who you're talking to.
Isn't there a package actually called Blender?
There's a 3D modeling software called Blender. I don't know if there's anything machine learning related about it.
Oh, I thought there was a stacking thing called Blender, but ironically, the one I'm thinking of, maybe it's not called Blender, but it does stacking, not blending. But maybe I'm thinking of the wrong thing.
One of my coworkers, his whole claim to fame, he was also Kaggle #1 for a while, but one of his big things is he wrote StackNet, which is basically this stacking software on steroids, where it can do many layers of stacking, and it keeps the validation in check and all of that stuff. So there's that. And that's the same definition that he uses in terms of blending and stacking and all of that. So I kind of defer to him because he's done so much with it.
Cool. Yeah, thanks everyone for the great feedback and discussion on this. So basically that was the end of the chapter, I guess. To just summarize, we covered 3 ensemble methods: bagging, boosting, and stacking. For voting, we talked about hard or soft voting, and we could sample either the training data or sample the features when building on ensemble. If you're building, like if you're just focusing on trees, you could use random forest. And for boosting, we covered 2 algorithms: adder boost and gradient boosting. And stacking is just having another model to learn to perform the aggregation. And yes, that's basically what the chapter had.
Yeah, really nice job, Nidhin. The author mentions feature importance for random forest. I'm pretty sure all of the boosting packages I've seen also have a straightforward output for feature importance, like XGBoost and Light GBM. I think they all also do that. So if that's one of the things that you care about, I would say, despite the fact the book doesn't mention it, that's not a reason to use random forest over gradient boosting. I think they'll all give you feature importance.
Oh yeah, that's true. Yeah. Cool. I'll stop sharing. Thanks, everyone.
Yeah, really awesome. Any other questions or just comments about this material? All right, going once, going twice. So everybody's done a really, really good job. Thanks again, Nidhin. Everyone's done a really good job with the preparation, the slides, the notes. I'm really, really appreciating all the work that you guys are putting into these discussions. I think it's going really well. So we've got a little less than 15 minutes until Ryan's event. So I don't know if we want to just do another quick breakout. If people just a little bit of time. We're not going to start early because I think there's some people who aren't in this meetup who are coming at 1:30. So unless anybody has any other ideas, I think that's probably the easiest way to go. All right, so Ryan, you can stop the recording and